Standard temperature and pressure, otherwise known as STP, has a set of specific values for temperature and pressure, and they are 0 degrees Celsius or 273 Kelvin. Of course, you know all gas laws are always done in Kelvin, and 1 atmosphere or 760 millimeters mercury. Now, when we have these specific values for temperature and pressure, we will get a conversion factor, 22.4 liters per mole. We get this conversion factor, and it's a conversion factor because it has a set of units on the top and set of units on the bottom. And so with this conversion factor, we can go from moles of a gas to liters of a gas, and from liters of a gas to moles of a gas. And in words, we would say that a mole of any gas is 22.4 liters. So a mole of any gas is 22.4 liters. This is a very handy conversion when you're going back and forth between moles and liters. It actually comes from the ideal gas law. And let me show you how it comes. Now, where does STP come from? Well, it comes from the ideal gas law, and so I'm going to go ahead and put that down. PV equals nRT. And I'm going to be looking for the volume because at STP, the volume 1 mole of gas is 22.4 liters. So I'm looking for the volume. So we're going to say volume is nRT over the pressure. Okay, so I have my gas law rearranged. So what are the values at STP? Well, at STP, I'm going to go with 1 atmosphere and 273 Kelvin. Now that gets us our number of moles is going to be 1 mole because we want per mole, per 1 mole. We want 22.4 liters per mole. And so I've got the temperature, I've got the pressure, I've got the number of moles. So now all that's left to do is pick our R, and since we're in atmospheres, this is what I want to do. I'm going to pick my R as being 0.0821 liters, atmospheres, moles, Kelvin. And so here we go. Here's all my values for a gas at STP, but we're not going to use our number for STP. We're going to use our ideal gas law, and we're going to get that number. And so let's go ahead and put this in here. And so we have 1 mole, because we want this per mole, 0.0821 liters, atmospheres, moles, Kelvin. And the temperature is going to be 273 Kelvin by definition for STP. And we're going to divide it by the pressure, which is 1 atmospheres. So at 1 atmosphere, 273 Kelvin, and 1 mole, let's see what our volume that we're going to get. And so we got 0.0821 times 273 divided by 1, and I get 22.4 liters. 22.4 liters, just like we predicted for STP. At STP, it's 22.4 liters per mole. .0 liters of methane gas, that's CH4, is 4.38 atmospheres at STP, standard temperature and pressure. How many mole CH4 gas do you have? Well, you see the STP, so that means that I know I'm going to need 22.4 liters per mole, because that's the whole point of STP, is you're going to get a conversion factor. Now, I don't see anything else going on up there, such as grams are going from, oh, I need to switch channels or something. I saw that binging and banging around. saw that. 16.0 liters of methane gas, CH4, is 4.38 atms, or atmospheres, at standard temperature and pressure, STP. How many moles CH4 gas do you have? Well, as soon as you see STP, or standard temperature and pressure, you know that you're going to need 22.4 liters per mole. This is the whole point of STP, is you have this conversion factor. And so this is how we go from liters to moles and moles to liters. And what are we trying to do here? We're trying to go from liters to moles, liters of methane gas to moles methane gas. So this is all we need for this problem. So we'll go ahead and set this up as a conversion. We draw a line. We draw another line. We always start with our measured number over here, up in this corner. That's my measured number, is 16.0 liters CH4. And now I can use my conversion factor here, which is STP. And so I want units to cancel. So what units have to be over here? They have to match up. Liters has to match up with liters so that it cancels. And so I'm going to take the STP value and I'm going to flip it over so that units cancel. So a mole CH4 methane is 22.4 liters CH4, or methane. And so now I have something I can put in my calculator. And so let's see, that would be 16.0 divided by 22.4, and that is 0.714 mole CH4. How many mole of 89.6 liters of hydrogen gas at STP? This is an STP problem because it says STP, so I need 22.4 liters per mole. STP, of course, is a way of going from moles to liters and liters to moles. And in this case, we are going from liters of hydrogen gas to moles of hydrogen gas. And so this is all we need for this problem. So we'll go ahead and draw a line, draw another line, and our measured number goes over here. That's our measured number. These STP problems are conversion factor problems, so we always start them out the same way. We start with our measured number up in the upper left-hand corner. And so now we need to use our STP number. And how are we going to use this? I want to match up the liters, and so I'm going to have to flip this over. And so a mole is 22.4 liters, and we can put this in our calculator. And that is 89.6 divided by 22.4, and I get 4.00 moles of hydrogen gas at STP. How many liters is 0.481 mole nitrogen gas at STP? Okay, well, this is an STP problem, so we would say 22.4 liters per mole. And that's how we go from liters to moles and moles to liters. I have so many moles, I'm going to liters. So let's go ahead and set this up as a conversion. And so our measured number is 0.481 mole. And that's our measured number. We always start with our measured number, and here's our STP conversion factor. We're going to take this, and we need to match up moles with moles so that they cancel. And I see moles is already on the bottom, so we'll use this like it is. And we'll put this in our calculator. So what would you have? Let's see, 0.481 times 22.4, and that is 18. That is 10.8. 10.8 liter of nitrogen gas at STP. So at 0.481 moles, we get 10.8 liters of nitrogen gas at STP. How many grams is 11.2 liters of oxygen gas at STP? Now the first thing I notice is that it's an STP problem, or standard temperature and pressure, so I know I'm going to need 22.4 liters per mole. Now there's another problem up here, and that is that we want the grams of O2. Now STP is away from going from moles to liters and liters to moles. It's not grams. Moles is not grams, but we should know how to get from grams to moles. And what do we need for that? We need the molar mass of O2, which is 2 times 16.0, which is 32.0 grams oxygen for every mole oxygen. In any problem that you see where you have grams, everything that has grams associated with it, you need the molar mass. If you see STP, you need the STP relationship for standard temperature and pressure. So now I have everything I need, I believe, to go ahead and get the grams of oxygen. So I'm going to draw a line because these STP problems are just big conversion problems. And so draw another line. What's our measured number up there? Well, this is our measured number, and it is 11.2 liters of oxygen gas. There we go. There's my measured number. Measured number always lives in the upper left-hand side. So we have a pair of conversion factors next. And what goes next? Well, what goes next is whatever has liters oxygen. Liters oxygen is our unit. It's our unit that we have to cancel. And so we need liters oxygen down here. And so I look, and I don't see liters over here, but I sure see liters over there, which means I'm going to use this as my next conversion factor, and I'm going to flip it over to get liters on the bottom so that liters cancel. And so a mole of any gas, and in this case it's O2, is 22.4 liters per mole. Okay, so now liters oxygen and liters oxygen have canceled. And so I put a check mark over this so that I don't end up reusing it. And so now I look for my other conversion factor, which is our molar mass, and we're matching up moles oxygen with moles oxygen. I see moles oxygen right there. And so I'm going to use my molar mass as a conversion factor, and I'm going to leave it like it is. And that would be 32.0 grams O2 for every mole O2. And we're set up, and I'm pretty sure I'm set up because I've got liters oxygen, I have moles oxygen, they cancel, we're left with grams oxygen. So let's put this in my calculator, and let's see what we get. 11.2 times 32 divided by 22.4, and I get 16.0 grams of oxygen at these conditions. How many liters of oxygen gas from 18.9 grams oxygen at STP? Well, the first thing I notice is that, of course, this is an STP, or standard temperature and pressure problem. So I'm going to need the conversion factor 22.4 liters per mole at some point. I also notice that I have grams oxygen. And any problem we do, whether it's gas laws or stoichiometry or whatever, if you have grams of something, you need the molar mass. And so I need the molar mass of oxygen, and that is 2 times 16.0 is 32.0 grams oxygen for every mole oxygen. So I have the molar mass, I have my conversion factor for STP. Time to set this up as a conversion. And so I draw a long line, draw another line, and we need to put our measured number here. There's my measured number. It's 18.9 grams of oxygen. Now, I need grams oxygen down here to cancel the grams oxygen over here. We need to be able to cancel. And so I look up here, of my two conversion factors, the one that has grams oxygen in it is this one right here. Now, to get grams oxygen to cancel, I'm going to have to take my molar mass and flip it over. And so a mole of oxygen gas is 32.0 grams of oxygen. I'm going to put a check mark over the top of that so I don't end up reusing my conversion factor. This is a small but important step to check them off as you use them. And so I'm not done here yet because I'm looking for how many liters, and I have moles oxygen here, which means I must have moles oxygen over here to cancel the moles oxygen, and the only thing I have left here that has moles in it is my gas Stp relationship. And so to get the moles to cancel, I'm going to leave this like it is. I'm going to leave it with the moles on the bottom, and so I'm going to say 22.4 liters oxygen for every mole oxygen, and we're done with my setup. Now we should always check to see that units cancel: grams oxygen, moles oxygen, moles oxygen. I'm left with liters oxygen, and that is indeed what I'm looking for, and there it is. And so let's put it in our calculator. Got 18.9 times 22.4 divided by 32, and I get 13.2 liters oxygen gas. 13.2 liters oxygen gas. We have this balanced equation up here. It's 4 aluminums solid plus 3 oxygen gases gives me 2 solid aluminum oxide. And here's the problem. What we want to know is how many liters of oxygen gas will you get from 17.2 grams of solid aluminum if the reaction is STP. Now this problem combines what we've learned from our stoichiometry or mass quantity calculations, and now we're combining that with gas calculations. Now there's a couple things that are going to have to happen here. We're going to have to pull down various bits of information from the problem before we can proceed. And so the first thing I notice that it says how many liters at STP, so I know I'm going to need 22.4 liters for every mole. Now, I also notice that I have grams aluminum. Now, I don't see grams anywhere else up here. So I need the molar mass for the aluminum. I know I'm going to need the molar mass. Anytime we have grams, you're going to have the molar mass. And that is 27.0 grams aluminum for every mole aluminum. Now the next piece that we have to have is that we're going from one thing to another thing, and anytime we go from one thing to another thing, we're going from aluminum to oxygen gas, we need the mole ratio. And where do we get the mole ratio? We get the mole ratio from the balanced equation. We have the balanced equation up here, and so I have aluminum, and so that would be 4 mole aluminum for every, now we got oxygen here, for every 3 mole oxygen. If you recall, to get the mole ratio, we just pull these numbers because this means 4 moles. This means 3 moles. So we have 4 moles aluminum to every 3 moles oxygen. And so we pulled everything down that I think I need to go ahead and set this up. So we're going to start with our measured number, and we're going to draw a long, long line. Because these problems, these mass quantity calculations and STP problems are all about canceling units. And so we're going to let our units do the setting up for us. And so we always start with our measured number. What's our measured number up here? Well, here it is, 17.2 grams aluminum. That's our measured number. 17.2 grams aluminum. And of course, it's always important to tag the grams, tag your units with what it is. This is not just grams, this is grams aluminum. And so now we'll get ready to let our units do the setting up for us. And so I have grams aluminum up here. I look at my 3 conversion factors up here, and which one has grams aluminum in it? It would be this one. This has gram aluminum in it. This is our molar mass. And so I need grams aluminum to cancel. I'm going to set up grams aluminum down here. So I need to flip over the molar mass, which is our conversion factor to go from grams to moles. And here we go. And so we draw another line, so I have canceled grams aluminum, now I have moles aluminum, and I've used this, so I better put a check mark over it so I don't reuse it. And so what's next up? Well, I've got moles aluminum, I'm going to need moles aluminum down here, and I look over here, and where do I see moles aluminum? Where do I see moles aluminum? I see it right here. Here's my moles aluminum. Okay, this is actually going to be the moles oxygen gas, liters oxygen gas right there. So I see moles aluminum and our mole ratio. So what do you think we should do? Well, I need moles aluminum, so I need to flip over the moles aluminum so it's on the bottom. 3 moles oxygen for every 4 mole aluminum. And I put a check mark over that as well. So now I've canceled the moles aluminum, I have moles oxygen. And so finally, the only thing left up here that has moles oxygen that I haven't used already is our Stp relationship, and that's 22.4 liters oxygen for every moles oxygen. I went ahead and put oxygen on it because that's the gas that we're looking for, that's the volume that we're looking for. And so let's see, I need the moles oxygen to be over here so that they cancel. And so I'm going to use this one like it is. I'm going to use that Stp relationship as is, liters oxygen for every mole oxygen. And there we are, it's set up. Now, how do I know for sure that it's set up? Well, one thing, we only use our conversion factors once, and we can check and be sure we got grams aluminum. I have moles aluminum canceling moles aluminum, moles oxygen canceling moles oxygen. I end up with liters oxygen. So let's go ahead and put this in our calculator. Let's see, I got 17.2 times 3 times 22.4 divided by, and I'm going to put this in parentheses, divided by parentheses 27.0 times 4. I'm going to close parentheses, and I'm going to get an answer. It's 10.7 liters. 10.7 liters oxygen gas at STP. At STP, how many grams ammonia, NH3, would you get from 14.2 liters of hydrogen gas? Now, this is a combination of stoichiometry mass quantity calculations and STP as a conversion factor. So the first thing I'm going to do, since I see STP up here, is I'm going to go ahead and write down my STP relationship. And so this is liters of hydrogen gas. It's because this is the one that is in liters, and I know I'm going to need it. Now, what we have to do is you also have to look up here, and anywhere where we see grams, I'm going to need the molar mass. And the only thing that I see that has grams on it is the grams NH3. So I'm going to need the molar mass of ammonia, NH3. So that's 14.0 plus 3 times 1.0, which is 17.0 grams ammonia for every mole NH3. 17.0 grams NH3 for every mole NH3. Now, I'm not quite done with my conversion factors yet, because in any mass quantity calculation, if you're going from one thing to another thing, you will need the mole ratio. And so I see that we're going from hydrogen gas to ammonia gas, and these are two different things that we're going between, and so the connection is our mole ratio, and that would have to be 2 mole ammonia, 2 mole ammonia for every 3 mole H2. And so where did I get this number? I got it from the balanced equation. This number came from the balanced equation. 3 mole hydrogen, 2 mole ammonia. There they are. And so I think I have all the pieces that I need, everything that's got grams. There was only one thing that had grams. I've got the molar mass. Since I'm going from one thing to another, I've got the mole ratio. And finally, since it's STP, I have my relationship, 22.4 liters per mole. I have that ready to go. And so let's go ahead and set this up as a big conversion, because that's how these stoichiometry STP problems typically end up being, is as a conversion. And so what's my measured number? Well, that's the measured number right there, 14.2 liters, H2. Now, we're going to let our units set up the problem for us. You really shouldn't try just memorizing some sort of setup. Let your units set it up for you. And so we're going to do that. So I have liters H2 here. I need liters H2 over here, and there's my STP relationship. It has liters H2. And since I need the liters H2 on the bottom over here, I'm going to flip my STP relationship. And so we're going to say a mole of H2 is 22.4 liters H2. And so we'll put a check mark over it just to make sure I don't accidentally reuse my conversion factor. And so what do we have here? We have moles H2, and we need moles H2 down here. And I look at my two remaining conversion factors, and this is the only one that has moles H2 in it. And so that was our mole ratio. And so since moles H2 is already on the bottom, and that's where we need it to be, is on the bottom, I'm going to use this mole ratio as is. I'm not going to do anything to it other than copy it back down here. And so that would be for every 3 mole H2. And so I'm going to put a check mark over this one. And so now I'm going to look and see that I need 2 moles NH3 here, because I need to cancel this unit over here. And the only thing left that has moles NH3, moles ammonia, is the molar mass of ammonia, NH3. And I see that moles NH3 is already on the bottom, so I'm going to use that molar mass as it is, 17.0 grams ammonia for every mole ammonia. And I should be done, but let's make sure that units cancel. And so sure enough, let's see, liters H2, that cancels. Moles H2, that cancels. Moles NH3, that cancels. We're left with grams ammonia, and it's what we want to know. How many grams ammonia would you expect? And so we get out our calculator, and let's see what we get. So we got 14.2 times 2 times 17 divided by parentheses 22.4 times 3 close parentheses equals, and I get 7.18 grams NH3 ammonia.